So this is the Michelson interferometer setup, and the helium laser, it is linearly polarized, and we have already used in this type of laser in Pokel's effect experiment. So here also we will use the helium neon laser to perform the Michelson interferometer experiment. Okay. So this is the beam splitter. Is it visible?
Yes, sir.
So this is the beam splitter. So when the light will incident here, it will be splitted in two ways. Okay, and it is 45-degree. It is aligned with 45-degree with this rotation, with the direction of the light, so that this reflection, so the incident ray and the reflected ray, this will be 90-degree. Okay, and it will transfer to the another and half part of this is reflected here, and half part of this will be transmitted. Okay, so transmitted directly. So it is M1 mirror 1. So we can see this. This is a mirror. Okay, so so half silver mirror, and this is another mirror. Okay, so this mirror is attached with the reducing gear, and this is separately situated. Okay, so uh, from here it will be reflected to this mirror, and it will be reflected back. Okay, and there the transmitted light will be reflected right here. So again the two lights. Okay, so one will be transmitted from this reflected beam, and one will be reflected to this through this beam splitter, and that will be collected here, and the interference pattern you can see. So we are switching off the light of the room, and we'll see how the interference pattern. So this is actually, so this alignment has actually been done before. So the in when you will be doing the experiments, you have to do it with yourself. Okay. So and now I'm switching on the laser. Okay. So you can see the pattern, right? Are you able to see the pattern?
Yes,
Yes.
sir.
Okay. So here again I will be discussing that this light ray, it is coming to the beam splitter, and here one part of it is reflected to this one, and as the angle of the beam splitter with the direction of the beam is 45-degree, so the angle of the incident ray and the reflected so incident beam and the reflected beam is 90-degree. Okay, so here you can see that the reflected beam is reflected again through this mirror, and the reflected from this mirror, that beam will be transmitted through the beam splitter again. Okay, and one part of the beam is was transmitted to that mirror, which is actually uh, associated with the reducing air. Okay, that beam, the transmitted beam will incident again with the in the beam splitter, and then it will be reflected back. Okay, so these two beams, which is been transmitted through this mirror and which is been reflected through this mirror. Okay, that beam will interfere, and you can see the interference pattern in the screen. Okay, so now go to that part. So the reducing gear. So here this is the reducing gear is to change the uh, uh, the beam path. Okay, so change the beam path. So the change in the beam path will be, you have already seen in the manual. It is called delta S. So delta S is the path difference which is being caused through this reducing gear. So what is when we rotate this one. Okay, So very low, very small portion of path difference will be generated. If we rotate directly here, the path difference will be greater, and we cannot identify the shift in the pattern. Okay, so now with this reducing here, so the path difference has been made very low. Okay, so now we'll mark here in a pattern. So we'll mark. So we are marking this one. Okay, we are marking this one. Now we'll rotate the reducing gear. Now we'll rotate the reducing gear. So you can see the change, and we have to count it. Okay, we have to rotate this very slowly, and we have to count. Just 3 have passed, 4. We have to do it very steadily so that we can count. So again, we are rotating. So 1. So we have to count the. Is it visible? No? And you can see the mark over the screen.
Yes, sir.
And you can see that fringe is moving, right?
Yes, sir. Yes.
And we have to count the movement. Okay, so the beam should be very steady. So the movement in the foot actually that will damaging the pattern. One, two, three, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So one rotation was there, and 15 fringes were shifted, right? So here the number of shift in the fringe, the number of count is 15, and one revolution will generate the path difference of 5 micrometer. Okay, so delta S is 5 micrometer here because we have done only one revolution here. Okay, so you know the equation Z, which has been count the number of count, and the lambda. The lambda is the wavelength of the light. So Z into lambda will be 2 into delta S, where delta S is the change in the path difference. So here the change in the path difference is one revolution is equivalent to 5 micrometer. Okay. So where these two that has been already discussed in the video which has been uploaded. Okay. So this is the thing, and we have to rotate it again and count for 2 revolutions. Okay. So up to this, any confusion? Any question after this? So like this, you have to rotate two revolutions, okay, of the reducing gear and count the shift in the fringes, okay. And accordingly, you have to calculate again. So you will get two wavelength of the lights, and you have to average it out, okay. So this is the experiment. So it is is it understood?
Yes, sir.
Yes, sir. Okay, so actually it can be aligned in a better way so that you will get more fringes here over this screen. Okay. Okay. Thank you. Thank you. We are closing the session now.
Okay, sir. Thank you.
Thank you, sir.
Thank you, sir.